Let us take a quick review of whatever we have done so far about integration. We started with the definition of what is meant by saying that a function is Riemann integrable or Riemann-Stieltjes integrable, and then we saw that using the definition we can decide about the integrability of a very few functions. So we come up with a criteria in terms of partitions how to decide whether a function is integrable or not, and then using that we proved several theorems about the integrability of functions, namely when the function is continuous it is integrable, when it is monotonic also it is integrable and things like that, and also theorems about the sums, products, etc. of the integrable functions. If you remember, we began with saying that you also learned integral for the first time as some kind of a reverse or inverse process of differentiation, but if you have seen our discussion so far, we have never referred to differentiation anywhere. Okay, there was no reference to differentiation. Okay, integral we have defined totally independently. So in order to establish that connection, we require one more thing, namely to view integral as a limit of sum. Okay, so that is what we shall do today, and then we will come to that connection between integrals and derivatives. Okay. So we first look at integral as a limit of a sum. Limit of a sum. Okay. Let us recall once again that we have defined what is called Riemann-Stieltjes sum, that is SPF alpha. As usual, f is a bounded function, alpha is a monotonically increasing function in some interval ab, and what was this defined as? This was defined as sigma I going from 1 to n f at ti and multiplied by delta alpha I, right, and till now we have not referred to this sum at all, really speaking. Okay. Whatever we have discussed about integrality and all, we discuss only in terms of the so called lower sums and upper sums. And but we have mentioned one thing, that relation between this and that is this, that is LP f alpha is always less than or equal to SP f alpha, and that is less than or equal to UP f alpha. Okay. Now what we want to define is what is meant by saying that the limit of this Riemann-Stieltjes sum exists. Okay, and what is the value of that? Okay. Let us recall once again that this point ti is any point in the interval xi minus 1 to xi. Okay. Alright, and let me again recall this definition. We have defined what is meant by mesh of the partition P. Okay. Mesh of the partition P, that was maximum value of delta xi. Okay, maximum value of delta xi. Okay, that is maximum of the length of the subinterval. Okay. So what we want to talk about now is that limit of this Riemann-Stieltjes sum as this mesh of P tends to 0. Okay. That is, this is what we want to talk, limit of SP f alpha as the mesh of the partition tends to 0. Okay. First of all, we shall define what is meant by this. Okay, what is meant by saying that this limit exists, and let us say its value is, okay, let us say its value is L. Okay, what is meant by saying this? As usual, we give this definition in terms of this epsilon, delta, etc. So what we would expect is, given any epsilon bigger than 0, there should exist some delta, okay, such that whenever the mesh of the partition is less than delta, the difference between the Riemann sum and this number L, that should be less than epsilon. Right. So that is okay. So let us write the definition. So definition. Okay, for every epsilon bigger than 0, there exists delta bigger than 0, such that what should happen for every partition P with mesh of P less than delta. Okay, that for every partition P, that for every P in this, remember the script P we have been denoting as the set of all partitions on AB. So every partition P with mesh of P less than delta, and one more thing, for every choice of Ti in this subinterval xi minus 1 to xi, okay, and for every choice ti in this subinterval xi minus 1 to xi, what must happen is the difference between this number L and this Riemann-Stieltjes sum, that should be less than epsilon, okay. Minus L, this should be less than epsilon, okay. If this happens, we will say that limit of this SPF alpha as mu p tends to 0 exists and its value is equal to L, and all that is written in this symbol, okay. Alright. Now if you notice that we have not defined the integrals in this fashion so far, okay. If you remember, our definition of integral was we have defined the upper integral as the infimum of the upper sums and lower integral as the supremum of the lower sums, and whenever those two coincide we say that that is the common value, that is what we call the integral, okay. Whereas, so what we should expect, or what that if not for all functions, at least under certain conditions, if this limit exists then the function should be integrable, okay, and the value of the integral should be same as this, okay. On the other hand, if the function is integrable, okay, then this limit should also exist, okay, and its value should be same as the value of the integral, okay, right. So this is what we want to if not for all functions, at least under some extra conditions, okay. So let us state that as a theorem. So as far as the first thing is concerned, we do not require, that is for one way we do not require any additional condition, okay, and that is the following: if this limit exists then the function is Riemann-Stieltjes integrable, okay, and this limit exists means this happens. Remember here, this is important, for every choice ti, okay, for every choice ti this should happen, that is the corresponding Riemann-Stieltjes sum minus L, that should be less than epsilon, okay, alright. So we will say that if, so that is the first statement, if limit as mu p tends to 0 SP f alpha equal to L, okay, that means the limit exists and it is equal to L, then f is integrable, f is Riemann-Stieltjes integrable, and the value of the integral is same as this limit, okay, the value of the integral is same as this limit, okay, and integral a to b f d alpha is equal to L, okay. Second part is the converse, but for the converse we require some additional condition, okay. For the converse, okay, I will come to the converse later. Let us first see how we prove this, okay. Okay, let us take the first part, okay. To show that something is integrable, we know what we need is, given any epsilon we should produce a partition P such that the difference between the corresponding upper and lower sum is less than epsilon. So let us start with that, okay. So let epsilon be bigger than 0, okay, alright. We know that this limit exists, so we apply this definition now, okay, okay. So for this epsilon there should exist some delta such that this should happen, okay, whatever we written here, this, okay. So then there exists delta bigger than 0 such that, okay, whatever I have written here, okay, such that for that if you take any partition with mesh of P less than delta, and for every Ti etc, this difference between the SPF alpha minus L is less than epsilon, okay, alright. Okay, choose one such partition, okay, choose one such partition, okay. Then for that partition, okay, that is choose a partition, let us let P be a partition with mesh of P less than delta, P partition such that mesh of P is less than delta. Then for this particular partition, the difference between this Riemann tilde sum and L should be less than epsilon, or which is same as saying that this should lie between L minus epsilon to L plus epsilon, right. Okay, let us write it like that. Okay, that is, let me say that then for every Ti, suppose this partition is P. Okay, let us say this partition is x0, x1, etc., xi. Then for every Ti in xi minus 1 to xi, what we must have is that let me write this Riemann sum, sigma I going from 1 to n. Let it, this time I shall write it in the full form. Instead of using this notation as Pf alpha, I shall write it as Fti into delta alpha I. This should be less than L plus epsilon and should be bigger than L minus epsilon. Okay. All right. Okay. Okay. Now the important point is this, that this must happen for every Ti. Okay. This must happen for every Ti in the interval xi minus 1 to xi. Okay. All right. So suppose I let Ti vary in the interval xi minus 1 to xi. Okay. Suppose I let Ti vary, then I can take the supremum over all such Ti here and say that sigma mi into delta alpha I is less than L plus epsilon, right, which is nothing but upper sum. Okay, right. Similarly, if I let Ti vary and take the infimum of the corresponding term, then I will get the lower sum. Okay, then I can say lower sum is less than L minus, bigger than L minus epsilon, right. So what we can say is this, basically what I am saying is this, let Ti vary in the interval xi minus 1 to xi for all I. That is, for each term, for each I you take all possible values of Ti in the interval xi minus 1 to xi, and all of them must be less than this L plus epsilon. So their supremum also must be, in fact, only thing that will happen is that when we take the supremum, this inequality may not remain strict. Instead of less than, you may have to replace it by less than or equal to. Okay, instead of less than, you may have to replace it by less than or equal to. Similarly here. Okay, is that clear? Okay, so then what we can say is this, then what we will get is L minus epsilon. This is okay, this will become less than or equal to LPF alpha. Okay, and this is less than or equal to UPF alpha, and this is less than or equal to L plus epsilon. Okay, right, but which is same as saying that UPF alpha minus LPF alpha, if you take the difference, that difference must be less than or equal to the difference between these two, L plus epsilon and L minus epsilon. Okay, and that is 2 epsilon. Okay, so we can say that is UPF alpha minus LPF alpha less than or equal to 2 epsilon, and that is okay, right. So suppose I had started right from here with instead of epsilon, suppose I had taken epsilon by 2 or epsilon by 3, you would have got here less than epsilon. So that is why we say that any constant multiple of epsilon is fine. Okay, that is, given any epsilon, you should produce a partition such that UPF alpha minus LPF alpha should be less. Okay, here you have less than or equal to, but does not matter, I can say this is less than 3 epsilon. Okay, right. So what does this show? It shows that the function is integrable. Okay, it shows, so because given any epsilon, we have produced a partition P such that for that partition UPF alpha minus LPF alpha is less than 3 epsilon. Okay, so that shows that f is integrable. Okay, this implies that f is okay. Now what remains? we also need to show this, okay, we also need to show this, okay, okay. Alright, we know that for every partition this number, whenever the function is integrable, for every partition this number must lie between upper sum and lower sum, right, okay, and so I can say that, so this number is somewhere here, okay, less than or equal to integral a to b f d alpha, okay, right, that is integral a to b f d alpha is bigger than or equal to L minus epsilon and less than or equal to L plus epsilon, okay. So what can we say, that means what can we say about the difference between that number and L? Difference must be less than or equal to 2 epsilon. So that is also, we can say that also integral a to b f d alpha minus L is less than or equal to 2 epsilon, okay, but epsilon was arbitrary, okay. So if this has to happen for every epsilon, this is anyway a non-negative number, it is absolute value, okay. So this is a standard technique, okay? Whenever, for example, whenever we want to set something is 0, one way is to show that it is less than every positive epsilon, okay, less than or equal to every positive epsilon. So that shows that these two must be equal, and which is same as saying this, okay, alright, okay. So we have proved that whenever this limit exists, the function must be integrable and the value of the integral must be same as this limit, okay. Now obvious question is the converse, okay. So suppose we know that the function is integrable, can we say that this limit exists and whether it equals the value of the integral, okay. Now there, as I said earlier, we cannot make that kind of a general statement. For example, what we would have liked to say is that if f is integrable, then this limit exists and it is equal to this integral, okay, right. We need to put some extra condition, okay, and there are various possibilities. One possible condition is that if f is integrable, sorry, if f has to be integrable anyway to talk about the converse, but in addition if f is continuous, then we can prove it this way, okay, or else if f is not continuous, then f is integrable and alpha is continuous, okay. So at least one of the function f or alpha should be continuous, then we can prove the converse also, okay. So let us just say, so if f is continuous, okay, let me split the conditions in two different ways, okay. Remember when we talk of a converse, what we have to think, that if f is integrable, then this limit exists, that is what we want to prove. But I want to say that we need some additional condition here. The first possible condition is that if f is continuous, if f is continuous, I do not have to say separately that it is integrable, okay, we already proved it, whenever it is continuous it is integrable, or f is integrable, f or a b alpha, and alpha is continuous, and alpha is continuous, okay, then this limit exists, that is then I want to say limit SP f alpha, limit as mu p tends to 0, this limit exists and its value is same as integral a to b f d alpha. That is, one of these two conditions has to be satisfied, either f is continuous or f is just integrable but alpha is continuous. Out of these two conditions, if f is continuous, it is fairly easy to prove, okay. In fact, you can say that bulk of the steps in the proof we have already discussed. What is the first step? First step is that if f is continuous, we know that since it is a closed bounded interval, it is a compact set, it is uniformly continuous. every continuous function is uniformly continuous on a compact set, that is something that we will use, okay. Then okay, let us look at this proof, okay. Let us say that let epsilon be bigger than 0, okay. Then to show that this limit exists, what we have to show, that there exists some delta such that if you take any partition with mesh of p less than delta, the difference between this and this should be less than epsilon, okay. That is what we need to show, okay, alright, okay. But since because of uniform continuity what exists, there exists delta bigger than 0 such that if x and y belong to AB and mod x minus y is less than delta, then mod fx minus fy is less than, okay. Instead of epsilon we will take something multiplied by epsilon here, okay. Okay, for the time being I shall call that number epsilon 1, okay. I will call that number epsilon 1, we shall choose that epsilon 1 later, okay, depending on what we require, alright, okay. Now okay, then what we know, what we can see from here, in fact this is how we proceeded with the proof. Since the difference between mod fx minus, so one can say that take any partition with mesh of p less than delta, okay, take any partition with mesh of p less than delta, okay. So let p belonging to p with mesh of p less than delta. Then what we want to show is that for such a partition p, the difference between the Riemann delta sum and this number integral a to b f d alpha, that is less than epsilon, okay, alright, okay. But what we know about this is the following, that if you look at for this partition u p f alpha minus l p f alpha, okay, then UPF alpha minus LPF alpha, that is nothing but sigma I going from 1 to n big mi minus small mi into delta alpha I, okay, alright. And big mi minus small mi, see that is, suppose now you take x and y in the interval xi minus 1 to xi, then since the mesh of the partition is less than delta, mod x minus y will be less than delta, right. That is, look at this ith interval xi minus 1 to xi, and suppose x and y both are in that interval, okay, then the difference between fx and fy must be less than epsilon 1, right, okay, which is but this must happen for every xy which lie in this interval, okay. So by taking supremum and infimum we can say that difference between mi, big mi minus small mi must be less than that number epsilon 1, okay, must be less than epsilon 1, okay. So we will take that epsilon 1 outside the summation sign, so it is epsilon 1 into sigma delta alpha I, something which we have done very often. So this is less than epsilon 1 into alpha b minus alpha a, okay. Okay. Now suppose I want this whole thing to be, let us say, less than epsilon or epsilon by 2 or whatever it is, I can take this epsilon 1 accordingly, okay. Okay. For example, so if I take this epsilon 1 as epsilon divided by alpha b minus alpha a, okay, then this will be nothing but epsilon, okay. That means UPF alpha minus LPF alpha is less than epsilon, okay. But this is not what we actually want to prove, right. Of course you can say that from this it follows that f is integrable, but that is something we already proved, okay. That is not our idea. Our idea is that we want to prove that this limit exists. But now what we notice is the following, that okay, this LPF alpha, this is, so you take any Riemann sum with respect to this partition, if you take any Riemann sum with respect, and for every choice of Ti, you can set LP f alpha less than or equal to SP f alpha and less than or equal to UP f alpha. Okay. This is something that we know always, whatever be the Ti. Okay. And what is one more thing that we know, that this number also lies between LP f alpha and UP f alpha. Okay. Right. That is also less than or equal to integral a to b f t alpha and less than or equal to UP f alpha. Okay. But what do we know? We know that the difference between this and this is less than epsilon. Okay. Just try to picture what is the situation. That is, let us say this is LPF alpha. You have this UPF alpha somewhere here. Okay. Right. This distance is less than epsilon. That is the difference between UPF alpha minus LPF alpha. That is less than epsilon. Okay. And both of these numbers, integral a to b f d alpha and this SP f alpha, both of them are lying in this interval. Okay. Both of those number, integral SP f alpha, integral f d alpha and this Riemann-Stieltjes sum, they are lying in this interval whose length is less than epsilon. Okay. So does it follow from here that the difference between them must be less than epsilon? Okay. So therefore integral a to b f d alpha minus SP f alpha, that is less than epsilon. Okay. And this is what we wanted to prove, right? So what we proved that given epsilon there exists a delta such that if you take any partition with mesh of p less than delta, then for that partition the difference between these two numbers is less than epsilon. Okay. And that is how we define, by saying that limit of, that is how we define this, that limit of SPF alpha as bu p tends to 0 is equal to L. Okay. So in this case the proof is somewhat easy. Here the proof is slightly involved because you are using the continuity of alpha instead of f. Okay. Right. And you have to also use the integrability of f. Something similar to one of the proofs that we discussed in other class. Okay. That is, you do not have control over all the entries in a sum. Okay. You have control over some entries, so there you do estimate in a particular manner and the remaining terms you estimate in some other way using the boundedness of the function, etc., and that is how we will have to do here also. Okay. The problem is here, that is because f is integrable, you can, given any epsilon, we can always find a partition such that for that partition the difference between UP f alpha and LP f alpha is less than epsilon. Okay. But the point is, to show that this limit exists, we have to show that for every partition whose mesh is less than delta, that same thing happens. Okay. But the mesh, suppose we knew that that partition is a refinement of this, then we could have said that earlier, but we could have said that using our earlier properties about the refinements. Okay. But the mesh is less than mesh of some other partition does not mean that that partition is a refinement. Okay. Because it may not contain those points, so that is why we need to do some extra work here. Okay. Okay. So let us now take this part. Okay. What are we assuming now? That f is integrable and alpha is continuous. Okay. Since here we need to use the boundedness of f, let us assume that suppose mod fx is less than or equal to some number k for every x in AB. This we can always say because we assume that f is Riemann integrable, f is integrable. So once the function is integrable, we are talking about integrability only about the bounded functions. Okay. All right. And let epsilon be bigger than 0. again we have to produce delta in that fashion. Okay. So first of all let us say that since okay, we will first use the integrability of f. Okay. Since f is integrable, and let us recall, so integral a to b f d alpha is also infimum of u p f alpha, okay, u p f alpha, right. So using this we can say that there exists a partition P, okay, suppose I call it partition P star. There is a partition P star such that u P star f alpha is less than integral a to b f d alpha plus, okay, let us say epsilon by 4, okay, something similar we had done in one of the proofs yesterday. Okay. See, this is infimum, so anything bigger than that is not an upper bound. Okay. So there should exist some partition such that upper sum with respect to that partition is less than integral a, less than this number, integral a to b f d alpha plus epsilon by 4. Okay. All right. Suppose this partition P star has n subintervals, let us say P star is x0, x1, x2, xn. Okay. One more thing, since we have assumed that alpha is continuous, okay, since we have assumed that alpha is continuous, alpha is also uniformly continuous in AB, okay, and hence what we can say is that there will always exist some delta 1, okay, such that if the difference between x and y is less than delta 1, difference between corresponding alpha x minus alpha y is less than whatever number we want. Okay. Okay. So we can also say that since alpha is uniformly continuous, on AB, there exists, okay, for the time being I will call that number delta 1, okay, there exists delta 1 bigger than 0 such that see, again we shall use a similar argument here. Okay. See, here what did we use, that whenever mod x minus y is less than delta, then mod fx minus fy is less than whatever number that we want there. Okay. So suppose we want apply this to alpha, what we can say is that if this length of this subinterval is small, then the corresponding value delta alpha I should be small. Okay. That is the idea. Okay. So there exists delta 1 such that if mesh of the partition P is less than delta 1, then delta alpha I is less than, okay, I want some number which depends on epsilon, so for the time being I will call that number eta. Okay. This eta we shall decide later. Okay. For the time being I will call that number eta. Okay. Then we take such partition, okay, we take such partition, so consider such P. Okay. Let P belonging to P with mesh of P less than delta. Okay. And here the argument is as follows, and consider this UPF alpha. Consider this UPF alpha. Okay. Now what we do here is that we compare this UPF alpha with this UP star F alpha. Okay. But the thing is, if we knew that P is a refinement of P star, I could have immediately said that UPF alpha is also less than this, but that is something that we do not know. Okay. That is something that we do not know, but what we know is that mesh of P is less than delta, so this delta, so we have a control over this delta alpha I. Okay. We have a control over this delta alpha I. Okay. And we do not have control over this thing. Okay. Now let me just try to explain to you, you can write the details there. How we are going to think of this is the following. Suppose this is the partition P, okay. Let us say I call this instead of x naught x1 x2, let us say P is y naught y1 etc. yn, okay. Now what is the idea here? There are two possibilities. Suppose you take any number, say yi minus 1 to yi, okay. This interval may contain one of the xi as an interior point. That is one possibility, okay. That is xi, that is yi minus 1 to yi may contain one of the xi's. That is one possibility, okay. What is the other possibility? That yi minus yi may not contain any of the points xi. If it does not contain any of the points xi, it means it is sub interval of one of the intervals here, right. Suppose yi minus this interval contains none of these xj's, okay, then it means it is contained in one of the sub intervals there, okay. If that is the case, then whatever contribution this will do to that upper sum, that contribution is already there here, or that is whatever is the supremum over this sub interval will be less than or equal to the supremum over whatever is the interval that is coming here, and that term is already here, okay. So if you take the contribution to the upper sum from those kinds of intervals, okay, then that will be less than this u p star f alpha, okay, that will be less than this u p star f alpha, okay. So I can say that u p f alpha, not the entire u p f alpha, okay, that is contribution to u p alpha due to those intervals which do not contain any of the x's, okay, that part of the sum that will be less than u p star f alpha, okay. This is slightly involved to understand, so just try to understand, okay. What remains then? Those intervals which contains one of these x's, okay, those intervals which contain one of these x's, okay. But you can say that in case of those intervals I cannot say that we cannot compare those with this term, but we can say what is the maximum possible contribution due to those intervals. There are two things, okay. You can say that there are at the most n minus 1 such intervals, right. Since the partition P contains this the points n plus 1 point, this x naught and xn are n points, okay. So the remaining points are n minus 1 points. So at the most n minus 1 of these subintervals can have one of these xj's as interior points, right. Is that clear? So we will estimate what is the maximum possible contribution from those intervals, okay. So since there are n minus 1 such intervals, we will say what is the maximum possible contribution from each interval and multiply that by n minus 1, okay, multiply that by n minus 1. So I said this plus n minus 1, okay, n minus 1 into, okay, what is the maximum possible contribution to this interval? You have to take the supremum over that subinterval, okay, we have to take the supremum over that subinterval. We do not know how it is related to this supremum, but we certainly know that it must be less than or equal to this number k, okay, because mod f x is less than or equal to k for all x in AB, okay. So obviously it must be less than or equal to this number k. So you can say n minus 1 into k, okay, and then because of this delta 1 we know that whenever mesh of P is less than delta 1, each of this delta, that is length of each of this subinterval is less than eta, okay, length of each of this subinterval is less than eta. So this must be less than eta, that is, okay, yes, yeah, okay. Did you follow the first part, that is those intervals? See, you take any interval corresponding to the partition P, okay, interval is yi minus 1 to yi, okay. There are two possibilities, okay, either this interval contains one of these xj's, okay, or it does not contain, okay. Suppose it does not contain, then it means this interval is contained in one of these intervals xj minus 1 to xj from here, okay, right, and hence the supremum over that subinterval will be less than or equal to the corresponding supremum over the corresponding interval there, and so that term is already coming here in this u p star f alpha, okay, okay. So whatever is the contribution due to those intervals, sum total of all those over those subintervals will be less than or equal to u p star f alpha, okay. So we need to see only the remaining intervals. What is the remaining intervals? Remaining intervals are the ones which contain xj is as one of the interior points, okay. But how many intervals can be there? Because there are only n minus 1 points here, okay, there are only x naught and xn cannot be interior point, okay, x naught is a and xn is b, so there are only n minus 1 points here, so there are only n minus 1 such intervals. Then supremum over each such interval must be less than or equal to this number, okay, because this is supremum over the whole interval, okay, and then multiplied by the length of that subinterval, but the length, not length, delta value, that is delta yi minus delta yi minus 1, but we have chosen this small delta 1 in such a way that that number must be less than eta, okay, that is where we have used the continuity of alpha, okay, that is where we have used the continuity of alpha and hence the uniform continuity of alpha, okay, that is if the mesh is less than this delta 1, then delta at yi minus delta at yi minus 1, that must be less than this number eta, okay. So the contribution due to the remaining n minus 1 intervals must be less than this, okay, okay, okay. Now at this point we can make a choice for this eta, okay, I said that I will not write eta value right now, we want to choose eta, we know that this is less than this integral a to b, this first term is less than integral a to b f d alpha plus epsilon by 4, okay, okay, and I will choose eta in such a way that this number also becomes less than epsilon by 4, okay. So choose for example eta is equal to epsilon divided by 4 into, okay, 4k n, let us say n minus 1 will do, but okay, we can choose something bigger than that also, okay. Suppose we choose eta is equal to epsilon by 4k n, then this whole thing will be less than integral a to b f d alpha plus epsilon by 2, okay. Now we have more or less completed the main idea of this proof. Just recall what have we proved? We have proved that given epsilon bigger than 0, there exists a number delta 1, okay, such that every partition with mesh of p, okay, this should be less than delta 1, mesh of p less than delta 1, okay, upper sum of that partition is less than integral a to b f d alpha plus epsilon by 2, okay, alright, okay. Can we make a similar statement about lower sums? Okay, we can say that similarly we can show that there exists delta 2 bigger than 0 such that for every partition P with mesh of P less than delta 2, we must have LPF alpha should be bigger than integral a to b f d alpha minus epsilon by 2, okay. What is to be done after this is obvious, okay. Choose delta to be minimum of these two, delta 1 and delta 2, okay. So let delta to be minimum of delta 1 delta 2, so this is also a positive number, okay. Then if you take any partition with mesh less than delta, then both of these things should happen, okay. Okay, so let P belonging to split P with mesh of P less than delta. Okay. Then for this partition P, UP f alpha should be less than integral a to b f d alpha plus epsilon by 2, and similarly LP f alpha must be bigger than integral a to b f d alpha minus epsilon by 2. Okay. So we can say that then for this P, then for this P, okay, let me start from here. Okay, integral a to b f d alpha minus epsilon by 2, this should be less than LP f alpha. Okay, and we know that any Riemann-Stieltjes sum is bigger than or equal to the lower sum. Okay, that is what we have seen already. So this LP f alpha must be less than or equal to SP f alpha, and then this is less than or equal to UP f alpha, and this is less than integral a to b f d alpha plus epsilon by 2. Okay, right. So what did we prove? That is, just take the whole summary. We start, given epsilon bigger than 0, we have given epsilon bigger than 0, we have got a delta such that whenever mesh of this partition is less than delta, all the sums of that partition are related by these inequalities. Okay, we only need actually this is less than SP of alpha, this is less than that. Okay, okay, that is the same as saying that integral a to b f d alpha minus SP f alpha, that is absolute value of this, is in fact less than epsilon by 2. Okay. Oh no, the difference that is less than epsilon. Okay, the difference between these two is less than epsilon. Okay, and that is what we wanted to prove. Okay. Okay, so let me again recall what did we prove, that if the limit of the Riemann sum exists as mesh P goes to 0, then the function is Riemann-Stieltjes integrable and the value of the integral is same as the limit of the sum. Okay. Conversely, we would have liked to prove that whenever the function is Riemann-Stieltjes integrable, then the limit of sum also exists and is equal to the value of the integral, but we have not proved it in that generality. We have assumed some extra condition, either f should be continuous or f is integrable but alpha is continuous. Okay, if at least one of these two conditions is satisfied, then we can assert the converse also, namely that the Riemann-Stieltjes limit of the Riemann-Stieltjes sum exists and the value of the limit is same as the value of the integral. Okay, all right. Now let us come back to the what I said right in the beginning, the relationship between integration and differentiation. Okay. So let us start with Riemann integrable functions first. Okay. So suppose f is Riemann integrable function. Okay. Then given any such f, we have seen that if f is Riemann integrable, okay, on the interval a b, then if you take any number c in the interval a to b, it is also integrable in the interval a to c. Okay, it is also integrable in the interval a to c. So what I can do is that I can say that you take any x, let x belonging to ab, then the function is also integrable in the interval a to x. Okay, in the interval a to x. So consider that interval, integral a to x, and let us consider this ft dt, integral a to x ft dt. Okay, then call this function big F of x. Okay, so define big F from ab to r by this. Okay, okay, then this function big F is differentiable. This function big F is, first of all, this function big F is continuous always, okay. This function big F is continuous always, and it is differentiable if this small f is continuous, that is whichever point this small f is continuous, at that point this function big F is differentiable, and the value of the derivative is same as the value of the function small f, okay. I will just write that, and then proof we shall discuss in the next class, okay. Then f is continuous on AB, okay. So next what we want to say is that further, if small f is continuous at x naught, at some point x naught in AB, then big F is differentiable at x naught, and the value of the derivative, that is big F prime at x naught, is equal to small f at x naught, okay. There is whichever point the function f is small f is continuous, at that point the function big F is differentiable, and its value of the derivative is same as small f. So this is a theorem which connects the ideas of integration and differentiation, and it, in a certain way, it shows that integration and differentiations are in some sense reverse processes of each other, okay. We shall discuss the proof in the next class.